2012 question 10A applied maths question. So this question is very similar to the ones we've been doing so far, except it doesn't have to do with speed and acceleration and displacement. It's got to do with rates of cooling. But just remember, the same rules apply, it's just different symbols you're using. So let's have a look at the information they gave us. Now, the questions are often not too bad maths wise, but there's always a little trick in the question that you need to look out for, or a little small hint or small kind of couple of words that really have an effect on the answer. So you need to be very, very careful when you're reading it. So Newton's law of cooling states that the rate of cooling of a body is proportional to the difference between the temperature of the body and the temperature of its surroundings. If theta is the difference between the temperature of the body and the temperature of its surroundings, then d theta dt equals minus k theta. So let's just think about that. They told us that theta is the difference, and it can be useful writing these things down, between temp of body and surroundings. So the first sentence here is the rate of cooling of a body is proportional to. Now this, you really want to understand this equation. So if the rate of cooling, that's how quickly theta is changing over time. And that's proportional to the temperature of the surroundings. Now because we're dealing with cooling, there's a minus in there as well, because this difference is getting smaller, it's not getting bigger. Now, just like in the previous questions that we've done, this is a proportional relationship. So in order to make it an equation, we put a k in there and we get minus k theta. So that's just where the equation is coming from. A body cools from 80 degrees to 60 degrees in 10 minutes. Find the temperature of the surroundings, or the temperature of the surroundings is maintained at 20 degrees. Find 1, the value of k. So here's the little small kind of trick that most people would miss in this question. If a body cools from 80 to 60, lots of people would say, well, their theta 1 will be 80 and theta 2 will be 60, our limits of integration. But what is theta again? Theta is the difference between the temperature of the body and the surroundings. So if the surroundings have a temperature of 20 degrees, theta 1 won't be 80, it'll be 80 minus 20, which is 60 degrees. That's the difference between the body's temperature and the surrounding temperature. Theta 2 similarly will be 60 minus 20, which is 40 degrees. The difference between the body's temperature and the surroundings. Our time 1 is obviously going to be 0, and time 2 is 10 minutes, because they said the body cools from 80 degrees to 60 degrees in 10 minutes. So now we have our limits, and that's the dog beside me making all that noise. Now we have the limits. Let's differentiate this equation. K is a constant, we've d theta on this side, so we will have 1 over theta d theta equals minus k dt. Now we can integrate both sides. Our initial temperature was 60, our final temperature was 40. Remember, don't just put the bigger number on the top, it's the initial at the bottom, what it goes to at the top. For t, we have 0 and 10. So here we're going to end up with log of theta 60, oh, wrong way around, just what I told you not to, 40 and 60 equals minus k, and that's just going to be t, 10 and 0, which is just going to be t. So that's log of 40 minus log of 60 equals, that'll just be minus 10k, because it's 10 minus 0. That's log of 40 over 60, our log rules, minus 10k. So k is going to equal log of 2 over 3, which is 40 over 60, divided by minus 10, which equals 0.2 0.0405. And that's part 1 answered. Okay, let's have a look at part 2. The temperature of the body after a further 15 minutes. And again, read the sentences very carefully. It's a further 15 minutes. So now our initial theta, and I'll go down here, theta 1 will be what it ended with in the first stage. So that's going to be 40. Theta 2 is what we're looking for. We're looking for the temperature after a further 15 minutes. We can call T1 0 again, and we can call T2 15, because it's like we're starting from scratch with these variables. So all we do now is go back to our equation, but now we know K, so we can find the missing temperature. So you can kind of pick where to go back to. You could go back to here and just put in your variables, or you could even have it differentiate. I'll go back to the very start. So we have 1 over theta d theta, and this time our limits are 40, and we're looking for theta, minus k dt, and our limits are 0 and 15. So we have log of theta and 40 equals minus 15k. That's log of theta minus log of 40 equals minus 15k, and we're just solving for k now. So log of theta equals minus 15k, and remember we know what k is, plus log of 40. Log of theta, type that into your calculator. You know the answer from k for part 1, and you should get 3.081. So therefore theta equals e to the power of 3.081, and that equals 21.78 degrees. Now, you think we're done, you think that's the final answer, but again, they tend to put little tricks in this. So it's the temperature of the body they're looking for. So what we've found out is we've found out theta, and theta, remember, is the difference in temperature. Sorry, I know that doesn't really look very neat. It's hard to write on this. So the actual temperature of the body would be the difference in temperature, which is 21.78, plus the temperature of the room, which is 20. So it's 41.78 degrees, and that's our answer.